from the University of Montpellier. So please go ahead.
Thank you very much, Gabriel. And first of all, I'd like to thank Gabriel and Suresh for organizing this workshop and inviting me to talk, to give a talk here. And I'd like to present here the results of a series of works, which are all listed here and which I did together with my remarkable collaborators. You can find here the names. So all these works, they concern model properties of some BPS indices which appear in Calabi-Yau compactifications of string theory, and how one can use these model properties to find these BPS indices and some other interesting quantities. Most of what I'll be talking about you can find in my recent review, and if I have time I also hope to present some work in progress which I'm doing with Albert Clem and Boris Pili. So let's start from general introduction, and first of all let me explain the setup and the problem which I'm going to solve. So we're considering type 2 string theory compactified in a Calabi-Yau threefold, and then in 4 dimensions we find effective theory which is described by n equal to supergravity. And in this theory, since it has an extended supersymmetry, there are half BPS states which are counted with sign by these BPS indices. And these BPS indices, they represent very important information about the theory. In particular, they have physical and mathematical incarnation. So from the physics point of view, for example, they count the number of states of half BPS black holes, which at microscopic level can be constructed as bound states of D6, D4, D2, and D0 branes, which wrap respectively 6, 4, 2, and 0 dimensional cycles. And they're characterized by an electromagnetic charge vector, which one can decompose in components, and then the components precisely corresponds to, like, the first component corresponds to D6 brane charge, the second to D4 brane charge, and so on. So in total, there are 2B2 plus 2 components of this electromagnetic charge vector, where B2 is the second Betti number of the Calabi-Yau, just because there are B2 plus 1 gauge fields, and each gauge field gives rise to one magnetic and one electric charge. And in the following, the index A will run from 1 to B2. Okay, this is on the physics side, and math side, it turns out that these indices, they coincide with a certain class of topological invariants characterizing the Calabi-Yau threefold, namely the so-called generalized Donaldson-Thomas invariants of the Calabi-Yau. And usually mathematicians characterize them by Chern classes of the corresponding covariant sheaf. So these invariants, they count stable covariant sheaves. But then there is a very simple, just linear transformation between what we use in physics, this electromagnetic charge, and the components of the Chern classes of the sheaf. I don't write it here, but it's really simple. So in the following, I will mostly use the electromagnetic charge. And this is a big problem to compute these BPS indices. And if we consider a limit of non-compact Calabi-Yaus, essentially then we reduce from supergravity to supersymmetric gauge theories, essentially. But then there are many techniques which in principle allow to compute this BPS index, like localization, using quivers, or some relations to some topological theories. But most of these techniques just do not work in the case of a compact Calabi-Yau. And nevertheless, this is precisely the problem which I would like to address in this talk: how to compute these BPS indices for computations on compact Calabi-Yaus. Before we go to this problem, let me tell you a few general facts, what we know about these Donaldson-Thomas invariants in general, so for generic Calabi-Yaus. And let's start from the simplest case, where our electromagnetic charge has just one non-vanishing component, namely corresponding to D0 brane charge. And then the situation is very simple. The result does not depend on this charge, and the invariant is always given by just earlier characteristic of the Calabi-Yau. The next case is when we switch on D2 brane charge. Then again, the invariant does not depend on D0 brane charge, so no Q0 dependence, and it's known to coincide with the genus 0 Gupa-Kumar-Waffe invariant of the Calabi-Yau. And you know that these Gupa-Kumar-Waffe invariants, they actually can be defined for arbitrary genus, and they can be found from define the topological string partition function associated with the Calabi-Yau threefold. And they can be found by solving this topological string theory using, for example, the so-called direct integration method, which is based on solving holomorphic anomaly equation satisfied by the topological string partition function. So this is a general method which works for generic Calabi-Yau, but there is a problem that when you solve this holomorphic anomaly equation, it's usually in such type of equations, the solution contains a holomorphic ambiguity, because you can add any holomorphic function to the solution and it still will be a solution. So you need somehow to fix this holomorphic ambiguity, and fortunately you need to so this holomorphic ambiguity is parameterized by just a finite number of parameters at each genus. So you do the solution genus by genus. Fortunately, we know some kind of boundary conditions which allow to fix these parameters. But the problem is that the number of known boundary conditions grows slowly, slower with the genus than the number of required conditions, than the number of parameters needed to fix the holomorphic ambiguity. And as a result, at some point, the two curves cross, and you do not have enough boundary conditions anymore, and you are stuck. So in other words, there is certain maximal genus up to which this direct integration method works, and you cannot go beyond this. So this will play an important role in my story later. Okay, so then this is about Gupa-Kumar-Waffe invariance, and then the next class of generalized DT invariants which I'd like to mention are just rank 1 and rank -1 invariants. So the role of the rank is played by the D6 brane charge, so P0, and then in the rank 1 case they're just the ordinary Donaldson-Thomas invariants, and in the -1 case they are called Podkhripand-Thomas invariants. And as you see here, I showed that they are parameterized by just two charges, this capital Q and small m. You can say, where is another charge? Because we expect D4, D2, and D0 charges. And here I have only kind of D2 and D0. So where is D4 brane charge? Well, the point is that these generalized Donaldson-Thomas invariants, they are known to be invariant under the so-called spectral flow transformation, which acts on charges in this particular way, where epsilon a's are arbitrary integers. And you see that if P0 is equal plus or minus 1, you can always set the D4 brane charge PA to 0. This is why the invariants do not depend on them, and the combinations which I wrote here, they stay invariant under this spectral flow transformation. So in the end, these two invariants depend just on two sets of charges. In the final set, and I forgot to say that actually there is a general relation between these DT and PT invariants and Gupa-Kumar-Waffe invariants, which is provided by the so-called MNOP formula due to Maulik, Nekrasov, Okhunkov, and Podkhripand, which allow to express one type of invariance through the other type. So if you know, let's say, all GV invariants, you can compute all DT and PT invariants. And the final type of BPS indices which I'll be interested in and which will play the K role in my story are the so-called D4, D2, D0 BPS indices. So in other words, I put D6 brane charge to 0, and therefore on the mass side, they're called rank 0 DT invariants. So in this case, also spectral flow invariance allows to reduce the number of charges on which these indices depend, but not completely. So here we can reduce dependence on the D0 on D2 brane charge, but we cannot completely remove it. there will be some remnant, which is this, which is called residue class, and which lives in this factor group. But the point is that whereas D2 branch charge could take any values, let's say integer values, this residue class takes only finite number of values, which and namely this number is given by the determinant of a quadratic form, which is defined by the intersection numbers in D4 branch charge. So in the end, our invariant depends on D4 branch charge, this residue class, which takes finite number of values, and the so-called invariant D0 branch charge, which stays invariant under the spectral flow. And therefore, we can form a generating function of these guys, which will depend only on D4 branch charge and this residue class. But since it takes a finite number of values, you can think about this as a parameterizing components of a vector. So you can think about this function HP as a vector valued function. And note that here I define it not using the original invariance omega, but the so-called rational invariance, which I denote by omega bar, which I defined like this. And the reason for this, it is because if I define generating functions like this, then they are expected to, and I will show you that they do possess some very non-trivial but very interesting modular properties, so more precisely mock modular properties, which are generalizations of the original modular properties derived by Maldacena, Strominger, and Witten many years ago. And the main claim of my talk is that using these modular properties, you can actually find many new invariants using the following procedure. So I'll briefly explain it here, but later I will expand on this. So you start by finding GV invariants using direct integration of topological string. Then you use a MNOP formula to get PT invariants. And then there are some non-trivial wall-crossing relations which allow to compute some finite number of rank 0 DT invariants, so this D4, D2, D0 bound states. And then the modularity actually allows, from the knowledge of a few such invariants, to find the full generating functions of these guys. At this point, you can even go back, and from the knowledge of this generating function, you can compute new PT invariants and new GV invariants, which will play the role of new boundary conditions for direct integration methods. So in this way, you can overcome the original limitations of this method. So the main conclusion is that this machinery, in the end, allows to compute many new BPS indices. Okay, so this is my general message. So now the concrete plan. So first, I will explain you the origin of modularity of rank 0 DT invariants and how they look like. Then I'll explain how the modular anomaly equation can be solved, at least in the one modulus case. And then I'll explain the procedure which I just briefly shown you on the previous slide. And in the end, I present some work in progress on the asymptotic growth of DT invariants. So first of all, why generating functions of rank 0 DT invariants should possess any modular properties at all? Because at first sight, we're dealing with generic Calabi-Yau. It doesn't have any elliptic fibration, okay, 3 fibration, for example, can take quintic, and it doesn't have any such vibration. So where is modularity comes from? Okay, so let me remind you that we're dealing type 2A on with the theory type 2A and Calabi-Yau. And let's compactify this setup on the additional circle, so that now we go to 3 dimensions, and in 3 dimensions, the effective theory can always be formulated as some nonlinear supersymmetric sigma model, which is characterized by certain target space, which I will call M. But now we know that type 2A is the same as M theory on the circle, so the whole setup is equivalent to M theory on a Calabi-Yau times 2 circles. But 2 circles is nothing else but the torus, and once you have torus in the game, it means that there must be modular group in the game. And the same conclusion you can arrive to the same conclusion if you just do T-duality along this additional circle, then you go to type 2b compactified on the same manifold. But you know that type 2b is invariant under S-duality. So again, there is a cell to Z modular group in the game, and somehow it must be reflected in this effective three-dimensional theory. And the claim that it is reflected in such a way that this manifold M, which one can call it modular space, it must carry an asymmetric action of this modular group SL to Z. Now, this is just one step. The second step is to note that we're dealing with D4 branes wrapped on some divisor of the Calabi-Yau. They describe this D4, D2, D0 bound states. And this still leaves one dimension uncompactified, so let's also wrap it on this additional circle S1. Of course, you can do it only in the Euclidean theory. And in the dual setups, this corresponds to D3 brane on the divisor and 2 brane on the divisor times the torus. So anyway, any of such objects, it looks like an instanton because it looks like zero. It has 0 dimensions in the it looks like 0-dimensional object in the uncompactified dimensions. And indeed, these instantons, they affect the theory. In particular, they affect the metric on this modular space M. They generate corrections which behave like this: the exponential minus the volume of the wrap divisor divided by G string. And what is important, they are all weighted by the BPS indices, omega of gamma. Just because this BPS indices essentially count the number of such objects. And what is good is that actually we know how all these instanton corrections look like, because more than 15 years ago, we provided historical construction of all these instantons. So you see, now we're in a situation where we have a metric on the modular space, which on one hand is affected by instantons, which depend on these BPS indices. And on the other hand, it must be invariant under SL to Z. And of course, this cannot be true for arbitrary BPS indices. So this SL to Z will impose certain restrictions on them. And the claim is that one can actually derive these restrictions explicitly. This is very non-trivial, but this can be done. And this is how the restriction look like. These restrictions look like. So to formulate them, I will introduce a certain function, which I will call h hat, and which is a deformation of my original generating function. So this is, so you add certain term, which is a bit complicated. I will explain it later, but first let me formulate the restriction. So it says that this function, which is now a non-holomorphic function of tau, depends also on tau bar, it must behave as a true modular form of this particular weight determined by the second Betti number of the Calabi-Yau. So it is this function which is called the modular completion of the original generating series, which must transform as a true modular. Well, the second term looks complicated, but the physical meaning is actually transparent. So if you see here, we have a sum of splittings of my D4 brane charge into components. So you can think about it as a sum of all bound states contributing to my BPS index. And the variable n is the number of the constituents of my BPS of my bound state, and then you take the product of generating functions of the constituents, and of course the most non-trivial piece is described by these coefficients r, which are non-holomorphic functions. I'm not going to present their precise form because it's a bit complicated, but roughly speaking, there's some non-holomorphic indefinite theta series with kernels constructed from sine functions, the so-called generalized terra functions, which are functions playing crucial role in constructing modular completions of indefinite theta series. So some complicated but explicitly known object. And you see that the crucial role is played by the variable n max, which is just the number of reducible components into which one can decompose our divisor GP. And in the following, I will denote this variable by small r. And depending on the value of this small r, we have two very different situations. If R is equal to 1, which means that my divisor is irreducible, the second term is absent. And the constraint just means that my original generating function must be a true modular form. More precisely, in this case, it's a weakly holomorphic vector-valued modular form. This is precisely the situation which was originally described by Maldacena, Strominger, and Witte. But if R is larger than 1, or in other words, my divisor is reducible, the second term is present, and its role is to cancel a modular anomaly of the original generating function. So in other words, the original generating function does have a non-trivial modular anomaly. And in fact, from the mathematical point of view, it's the so-called mock modular form of depth R minus 1. Well, this is just a name. You cannot do many things with the name, but what is more important, we have this equation which describes the precise modular properties of my generating functions. And actually, I can view this even as an equation on the generating functions, which allows to fix these functions up to certain ambiguity from the knowledge of this anomalous term. But before I'll show you how this anomaly equation can be solved, let me also mention that this anomaly equation already has many extensions and applications. Well, the first application already actually appeared in the process of deriving this equation, because it's in this process we actually solved a long-standing mathematical problem, how to construct modular completions of indefinite theta series. So this problem had a solution in the case of Lorentzian signature, where you have just one minus in the signature of the quadratic form, which defines indefinite series. But when there are more minuses, it was not known how to construct modular completions of such guys. And the solution came from string theory, because string theory kind of is it must be invariant under modular transformation just by construction, and therefore you don't need to guess anything, you just compute, and this is how these generalized error functions have been derived and modular completions of indefinite theta series have been constructed. Next, one can generalize the previous construction to include the so-called refinement parameter. Actually, for compact Calabi-Yau's, it's not clear whether it's well defined, but at least in the non-compact case, it is possible to do. So one can define the so-called refined BPS index just by replacing -1 by -y, where y is the refinement parameter. And then everything starts depending on this parameter. In particular, our generating functions will also depend on it. And it turns out that now, instead of being just mock modular forms, they become mock Jacobi forms, which satisfy an analogous equation. And actually, this analogous equation, it actually looks even simpler than the unrefined equation. And in these Jacobi forms, mock Jacobi forms, the role of the elliptic parameter is played by the logarithm of the refinement parameter. And next extension is actually, you can take the limit of non-compact Calabi-Yau, and if so, in particular, one can take the resulting non-compact Calabi-Yau to be just space of total fibration of the canonical bundle over a certain surface S, and if this surface S has Betti numbers like this, then it's actually known that this rank 0 dt invariance on this non-compact Calabi-Yau coincide with the Waffa-Witten invariance of this surface. And for SUN gauge group, and the variable n coincides with the just degree of reducibility of the divisor, and the role of the divisor is played by this surface S. So essentially, we take D4, D2, D0 bound states where D4 brane is wrapped on surface S n times, and this and the corresponding run 0 dt invariant coincides with the SUN Vafa-Witten invariant on the surface S. So that's the claim. And then since they coincide, it means that this Vafa-Witten invariant satisfies the same anomaly equations which I showed you before, and the same holds also in the refined case. And the claim is that you can use this information to actually find explicitly the generating functions of this refined Vafa-Witten invariance on several rational surfaces like P2, Hirzebruch, and Delpezzo. And another completely unexpected extension of this setup we did with Suresh a few years ago. It turns out that although the original setup just describes computations with n equal 2 supersymmetry, but it turns out that even computifications with high supersymmetry, like n equal 4 and n equal 8, they also fit the same framework. Essentially, the corresponding generating functions of BPS indices preserving different supersymmetries, they all satisfy the same equation, which essentially I showed you before. And even we use this fact to generalize the famous holomorphic anomaly equation, which was derived by Tabulkar, Murti, and Zagia for in the case of for immortal dynes in n equal 4 computations. We generalize it to the case of non-trivial torsion invariant. But you see, most of these results, they concern, well, for example, non-compact Calabi-Yau's. But as I told you in the beginning, the real problem which I'm interested in is to treat the case of compact Calabi-Yau's. So the challenge is really, can we apply these anomaly equations to get some new information about compact Calabi-Yau's? And here, so this is the goal. Try to find the generating functions using these model properties which I described before. And here again, we should distinguish two cases. So in the case of irreducible divisor, our generating functions, remind you, is a weakly holomorphic modular form. And in this case, the procedure is kind of simple because the space of such functions is finite dimensional, and moreover is known to be the dimension of the space is known to be bounded from above by the number of polar terms. The polar terms are just the terms in the Fourier expansion of generating function with negative power of the modular parameter q. So it means that if we know the coefficients of these polar terms, we can fix the generating function uniquely. And actually, this procedure has been used already many years ago to address this problem, but the methods which these people used were not well. They were specific for the Calabi-Yau's under consideration, and only very few Calabi-Yau's have been treated, well, and even for some of them, the results were controversial. So some results were different. I mean, different groups found different results for some Calabi-Yau's. Now, the next case is when we take the divisor to be reducible. And then our generating function is already a mock modular form. And here, just this procedure is already not enough, and we should proceed in two steps. So as a first step, we need to solve our modular anomaly equation and just find any solution satisfying this equation. And of course, if you find such a solution, then our true generating function can still differ from this solution by a holomorphic modular form, because then if you add such term, it will still satisfy the anomaly equation. So we have this kind of holomorphic modular ambiguity, which we need to fix. And this will be our second step. But here you can fix it already by just exactly in the same way as in the case of irreducible divisor, because we just need to fix a modular form. And this can be done by finding polar coefficients of my generating series. So first solve modular anomaly equation and then find polar coefficients to fix the modular ambiguity. That's the procedure. And at least the first step, namely the solution of modular anomaly, has been done. I did it recently with my PhD student, Khalil bin Riz, in the case of one modulus Calabi-Yau's, namely three folds with Betti number B2 equal to 1. So in that case, we found generic solution of the modular anomaly equation. Actually, the solution is quite complicated. So it's constructed from indefinite theta series and the so-called Jacobi-like forms. And it looks complicated, but it looks complicated because we really wanted to find general solution and treated simultaneously the whole degree of reducibility, this small r. So we found solution for any r. But if you specify to the case, for example, of r equal 2, then you don't need this general solution which we constructed. So then there are simple solutions. So let me show you how this case can be solved in a very, very simple way. So in this case, r equal 2, and if we restrict to one modulus Calabi-Yau's, then our function h2 is a mixed mock modular form of weight minus 3/2. And it must satisfy the following holomorphic anomaly. So its completion must satisfy the following holomorphic anomaly equation. So you just take anti-holomorphic derivative of the equation, which my general equation, which I showed you before. And you see that the anomaly is described in a very simple way. So there are just two factors of h1, just because 1 plus 1 is equal to 2. And the coefficient is given by a very simple unary theta series. The complication here is that this is a mixed mock modular form, which means that the shadow is a product of holomorphic and anti-holomorphic modular forms. But you can disentangle this mixed nature of generating function by postulating the following ansatz, just where capital G is are the functions to be found. And then if you plug in this ansatz into this equation, you find that this capital G it must be already usual, not mixed, usual mock modular form, satisfying very simple holomorphic anomaly equation. So it just means that the shadow of this capital G is this unary theta series. And it turns out that exactly the same problem has been solved in this famous paper by Dabholkar, Murthy, and Zaghia, which I already mentioned, because they tried to find precisely such mock model forms with an additional requirement that they must have slowest possible growth for their Fourier coefficients. We do not care about this additional property, but since they already found a solution and we're interested in any solution, so we can just take that solution. And the solution is constructed from certain Hecke-like operators and some set of very simple functions, which I denote here QD, and which appear just for D whose Möbius function is equal to 1. So which means that these are numbers like 1, 6, 10, 12, and so on. But for example, if you take function Q1, which is just generating function of Hurwitz class numbers, which is like the most canonical object in the theory of mock model forms, and apply to it some Hecke operator, this is enough to describe like all cases with intersection number of Calabi-Yau equal 1, 2, 3, 4, 5, 7, 8, 9, and so on. So you see, so you immediately get for free the solution. So no complications here. Okay, so
can I ask a question here? Sorry, Sergei, may I? So in the case that R is bigger than 2, how does the structure of that anomaly equation change? Is there a big change to the anomaly equation? Is the structure similar, or?
Well, the structure is similar in the sense there will be still like H1, H2, for example, also term with H1, H1, H1. Mm-hmm. But the problem is that the coefficients here become more complicated. So that's the main trouble. So in particular, they and they will involve these generalized error functions.
Okay, but you have a general expression for that.
Yes, yeah.
Thanks.
Okay. So given that we solved this, so let's restrict in the following to this one model's case. So then we have solved this modular anomaly equation, and this reduces the whole problem to finding just the polar terms. But this problem is actually quite non-trivial. And the general approach to it is to the general idea how it can be solved is using to use the so-called wall crossing. So I remind you that wall crossing, the phenomenon that actually our BPS indices, they are not constant throughout the modular space, they're only piecewise constant, but they can jump across certain codimension one walls in the modular space. And the physical reason for this is very simple, because our BPS indices count not only single-centered black holes, but also multi-centered black holes. And bound states can be stable in one region of the modular space or unstable in the other region. And that's the reason for these jumps. And whether something is stable or unstable is described by the so-called stability condition. And it's known that this stability condition is completely determined by the central charge function, which is a function which is linear in charges. So this Q lambda and P lambda, and with the coefficients determined by the Keller moduli. So Z lambda are our Keller moduli, and F lambda are derivatives of the holomorphic prepotential on the Keller modular space, which is also a function of the Keller model. Okay. And the good news is that actually we know how to cross walls, at least in principle, because these BPS indices, they satisfy the Kontsevich-Stoibelman or Joyce-Sonk wall crossing formulas. So at least in principle, we can start in any point in the modular space and go to the chamber which we are really interested in. And yeah, I didn't tell you before, but the BPS indices which we want to compute are those, and for those for which we expect modular properties, are BPS indices evaluated in the so-called large volume attractor chamber. So there is particular chamber in the modular space we're interested in, but in principle we can start in any place and do this wall crossing. And this gives us the idea that, okay, let's find the chamber in the modular space with sufficiently simple BPS spectrum, compute it there, and then do wall crossing. And precisely this idea actually very often works in the case of supersymmetric gauge theories. But it does not work in supergravity, because in supergravity there are no chambers with simple BPS spectrum. All chambers are very complicated. But here mathematicians come to rescue us, because what they suggest is that actually one can consider so if you're interested in all stability conditions, so we can think about modular space as kind of space of stability conditions because they're parameterized by the moduli. But actually, the space of all stability conditions is larger than just the Keller modular space. Because what we can do, we can take these coefficients of lambda to be independent parameters, not to be fixed by the prepotential, but to be completely independent. In this way, we enlarge the space of stability conditions, and it becomes larger than the Keller modular space. And the Keller modular space then will be just a kind of slice in this big space of all stability conditions, which is called Bridgian stability conditions. And it turns out that in this larger space, there are other slices, which are somewhat nicer. In particular, there is a so-called new BW stability, which is a slice lying somewhere at the boundary on this large space, which possesses some nice property. Namely, it turns out that there is a region somewhere here where some BPS indices actually are known to be vanishing. And then the idea is very simple. Let's just start in this chamber of the modular space and do wall crossing towards this large volume attractor chamber, which is somewhere here. And since in this chamber, this new BW stability is exactly the same as the physical stability, just performing the wall crossing, we will be able to find the physical BPS index which we are interested in. And precisely this idea has been realized, and it leads to explicit formulas relating PT invariants, which I mentioned in the beginning of my talk, which are rank -1 generalized DT invariants and rank 0 DT invariants, which we are really interested in. So let me briefly show you how this formula looks like. Well, it's very simple. So you start with PT invariant, which is known to vanish with respect to this new BW stability somewhere far from the large volume, and then you do just wall crossing, and it turns out that it's enough to apply just the primitive wall crossing formula. So in the end, this PT invariant is expressed as a sum of a bound states where the components are again anti-D6, D2, D0 bound state, which gives a PT invariant, and D4, D2, D0 bound state, which gives our rank 0 DT invariant. And importantly, this does not work for any PT invariant because you need to satisfy this condition that it vanishes in this chamber, original chamber. And another condition is that on the way towards the large volume, only bound states with D4 branch equal 1 appear. This also imposes certain condition. And so both conditions are encoded in this inequality. So, and then the claim, if this inequality is satisfied, there is a formula like this. Of course, the most important information here is in the range of summation over Q prime and M prime, which I don't indicate, but there are two important properties about this set, which you sum over. First of all, Q prime is always less than Q, which means that the formula is recursive, namely PT invariant is determined by PT invariance of lower charges. And secondly, there is all this term with Q prime and prime equal to 0, for which PT invariant is equal to 1, which means that there is a term which has just this rank 0 DT invariant. And then you can put it on the left, this PT invariant, put it on the right, and in this way, you get a formula for a rank 0 DT invariant, expressing it in terms of PT invariance. And another interesting feature is actually you can write such a formula for any charge of rank 0 DT invariant. You can ask how is it possible, because first here I have a certain condition on charges, but the point is that rank 0 DT invariant are invariant under the spectral flow transformation, and you can apply the spectral flow in such a way that after the transformation, the charges always satisfy this inequality. So in other words, for any charge one of rank 0 DT invariant, you can write such kind of formula expressing it through PT invariance. And moreover, a similar formula also has been derived when the D4 branch charge is equal to not only to 1, like here, but also to 2. So in this way, we expressed D4, D2, D0 BPS indices through PT invariance. But how to find these guys? Well, and here we use this MNOP formula, which I mentioned in the beginning of my talk, which expresses it through GV invariance, and this GV invariance in turn can be found using direct integration. So here, just I wanted to recall you this MNOP formula. So first we have Gopakumar-Waffe representation of topological string partition function. Then we define just stupidly the generating function of PT invariance. And then the claim is that the two generating functions are related by this type of formula. So you just change the parameters in a proper way and multiply by a certain power of the so-called McMahon function. And that's it. And as a result, we arrive at the procedure which I already showed you in the beginning. So we first do direct integration of topological string, find GV invariance, apply this formula to get rank -1 DT invariance, then this wall crossing formula which I showed you on the previous slide. In this way, we compute rank 0 DT invariance, and if we compute sufficient number of them, namely so that we can cover all polar terms in the generating function, then modularity allows to find the full generating function. But here there is a restriction, which I also mentioned in the beginning, that this direct integration works only up to some genus, which I call Gmax. And this means that also PT invariance can be computed only up to a certain degree and not higher. And in turn, this also imposes on restriction the number of rank 0 DT invariants which we can compute. And this is why this procedure is not universal. It cannot be applied to arbitrary Calabi-Yau, arbitrary charge, D2D0 BPS index with arbitrary charge. Unfortunately not, because this restriction on the maximal genus which we compute. Nevertheless, so what we considered, we started a set of complete intersection Calabi-Yaus with one Köhler modulus. There are 13 such Calabi-Yaus, and for 11 of them, we succeeded to compute all polar terms, which means that we found these generating functions H1, so with 1 unit of de Forbren charge. And moreover, for 2 of them, we managed to also compute the case of de Forbren charge equal to 2. And whereas these guys are the usual modular forms, these guys, H2, I recall you, they're already mock modular forms. And I believe this is the first example of a mock modular form associated to a Calabi-Yau without any specific internal structure, like, for example, elliptic fibration. In fact, we could do even better. We computed not only polar terms, but also many non-polar terms using these wall-crossing equations. And they perfectly matched the prediction of modularity. Because the same non-polar terms you can obtain just by expanding the generating functions, right? And it's really striking to see how huge numbers, sometimes with 30 digits, they perfectly match and being computed from completely two different methods. And I should say that from the mathematics point of view, this modularity is completely mysterious. So it's really very non-trivial check of the physical prediction of modularity from string theory. And of course, you can expand, once you know generating function, you can expand them to arbitrary order. And in this way, we get predictions for infinitely many rank 0 DT invariants. And from this point, as I also mentioned in the introduction, you can go back and using the knowledge of this rank 0 DT invariants, you can compute some PT invariants and some GV invariants. And they will surface in new boundary conditions for direct integration method. And in this way, you can now go further and compute GV invariants beyond this Gmax. Just to give you a couple of examples, for the famous quintic manifold, the original restriction of direct integration was genus equal 53, and we already computed up to genus 64. And the so-called decantic manifold, this is a case where we could go to charge equal 2. So the original restriction genus was 50, and we already achieved 71.
Can I ask a question here? Sorry,
sure.
Can I ask a question? So these new boundary conditions, is there some structure behind them? I mean, other than the way you generated them, is there something striking about them? Can you say something? Is there something noticeable about them?
No, we just, these are values of sum of GV invariants.
Okay.
So just we are able to compute some GV invariants for each genus, and well, sometimes they enough to fix completely the holomorphic ambiguity. Also, it's not that we can go to infinity. So no, unfortunately, we get kind of new restriction, if you wish, Gmax modified, right? So if we know H1s, for example, we get this new for quintic, the restriction, I don't remember, it will be like 70 probably. If we were able to compute H2 for quintic, then we could go up to 100 maybe. So okay. It's like this. So each knowledge of each new generating function allows to go further and further in this direct integration method. Here I just flashed the results for this decantic manifold where we know both H1 and H2, and you see H1 is just, well, it's a scalar function. So it has just two polar terms, and well, it's simply given by Eisenstein series and the Dedekind data functions. And for H2, well, we also know the explicit expression in terms of this generating function of Hurwitz class numbers, which I mentioned a few slides ago, but well, I just didn't show it here, but we can generate expansion up to arbitrary order, and here I just showed a few terms, and you see that it's already a vector valued function, and it's a modular form. Okay, so I think I still have 10 minutes, so if there are no more questions about this, maybe I can present results of an ongoing work about asymptotics of all these topological invariants. The point of our work is that, well, you see, we were able to compute many BPS indices, many topological invariants of Calabi-Yau manifolds like GV, PT, DT invariants, and so we generated big tables of these topological invariants. And once we generated these big tables, we can try to study numerically, for example, their asymptotics. And you know, for asymptotics, there are also predictions, very often analytic predictions from Wittgenstein-Hawking formula or some other results. So we can try to compare with the analytic predictions, or maybe to get also something interesting. Before I present these results which we obtained, let me first show you how typical table of such invariants look like. So for example, this is a table of GV invariants for one of the manifolds. And you see that, so here we have genus which grows if you go down, and degree if you go to the right. And you see that for fixed degree, at some point, all GV invariants just equal to 0. This is the so-called Castelnova bound, which all GV invariants should satisfy. So the genus is restricted from above by a quadratic polynomial in the degree. And in particular, this implies that there is a restriction, because we restriction the maximal genus for which we can compute GV invariants, and this also generates the restriction maximal degree for which all GV invariants are known. And this is important for us because typically we will be interested in the asymptotics of large degree. And just from this Castelnova bound, you can get this. And just here I showed that the best case which we have with respect to degree is the manifold X for 2. Because here you see it's an interplay between intersection number of the Calabi-Yau and the maximal genus up to which we can compute GV invariants. And for this manifold, they are both sufficiently big. So kappa equals 6, and this G available is 64. So we can go up to degree 28. For example, for quintic, you see it's they are less for quintic and decantic because the intersection numbers are less. So let's first consider the asymptotics of BPS indices of 5-dimensional rotating black holes, which are known to be captured by GV invariants like this. And let's just plot the logarithm of absolute values of all these indices. And you see, you find for sufficiently large degree almost smooth curves, but there is some striking kink appearing here. Actually, this kink has been observed already a couple of years ago but in the paper of Haider and Lin, and they provided a very beautiful interpretation of this phenomenon. Namely, it is a certain phase transition which happens because entropically here black holes are dominating, and in this region black rings which exist in 5 dimensions and which topologically are different black objects than black holes, they start having a larger entropy. So there is this beautiful phenomenon, and we also confirm it from our tables of GV invariants. Now let's do the same for PT invariance. Let's plot PT invariance, again, for as large degree as possible. And here we find also some striking behavior, which is actually confirmed for almost all Calabi-Yaos. So here we find kind of the same kink, first of all. So, and actually it can be interpreted in the same way, because, you know, there is a relation between 5-dimensional black holes and 4-dimensional black holes. And so one can just translate the results of Heider-Lin to the 4-dimensional case. So then it means that here the main contributions come from multi-centered black holes, which represent bound states of D6 and D40 to D0. And here the contributions come from single-centered black holes. But then again, there are two completely new behaviors which arise. So first, there is certain plateau where the PT invariant is almost constant, and then they start growing kind of logarithmically. And we even were able to derive approximate expressions for the invariance in these two regions, just using MNOP formula. But what is completely mysterious to us is microscopic interpretation of these results. So what does it mean? What are the objects, kind of black holes or some bound states, which kind of provide these main contributions to, and which determine this behavior? So that's a complete mystery to us. One can do a similar thing also for usual DT invariants, but here it's a bit more boring because, well, if you look at the relation between DT and PT invariants, it's provided by just the power of McMahon function, and it turns out that this McMahon function completely kind of wins in this. It completely determines the asymptotic behavior for large angular momentum or large D0 brane charge. So that's how DT invariants behave. So there is no plateau, there is no, well, kind of logarithmic behavior, but it's completely determined by this McMahon function. And another interesting observation, which I'd like to mention, is that these kind of phase transitions, you can see them also in the behavior of the sign of all these invariants. Because here I plotted just the logarithm of the absolute value, but if you look at the signs, for example, let's look at the signs of PT invariant. Then you see that in the first region, so here, the sign is alternating. So it's plus and minus. Then it becomes just positive. And then when you go to the plateau, it becomes just negative. And then when this logarithmic curve rises, it becomes again alternating. So somehow these phase transitions are also correlated with the behavior of the sign of topological invariance. But again, we do not have any interpretation of this behavior. These are just, if you wish, numerical observations. What they mean, we do not know. Okay, so my time is almost over, so let me just finish and with conclusions. So the main message which I would like to tell you is that we derived modular properties of generating functions of D40 to D0 BPS indices, or from the math side, rank 0 DT invariants. And this anomaly equation, it actually has numerous extensions and applications, and at least in the one model's case, it can be completely solved, and which reduces the problem to finding just a finite number of polar terms. And these polar terms have been found for some set of examples using modularity while crossing direct integration of topological string, which produced explicit mock model forms describing the generating functions of rank 0 DT invariants, and maybe even more importantly, it allowed to overcome limitations of the direct integration method of for solution of topological string. Well, I also showed you some new results about asymptotics of this invariance, and which indicates the existence of some phase transitions, but its interpretation is unclear to us. And of course, one can imagine some obvious extensions of what we have done. In particular, of course, it would be interesting to compute polar terms and in this way to fix generating functions for other cases, in particular for higher deforming charges. But here it looks like we need a new strategy, because the strategy which I explained to you is very demanding on the knowledge of GV invariance. And there we have, you see, these limitations of the direct integration method. So probably we can try to find some other wall crossing relations which will not be so demanding. And of course, one can try to consider also Calabi-Yau's with 2 or more moduli, and maybe even try to obtain results for DT invariants of higher ranks. But we do not expect that they possess any modular properties, but still they satisfy nice wall crossing relations. So maybe one can derive systematic procedure for to compute them. So let me stop here, and thank you very much for your attention.
Thanks very much, Sergei, for this very nice talk. Thanks. Are there any questions?